Take 4. So in this short tutorial, we're going to summarize some of the key aspects of phase changes in terms of energies, molecular separation, and an effect on the surroundings. That's an aspect that you wouldn't normally associate with phase changes, but it's something we want to be aware of. And then lastly, we're going to finish up with a phase change that doesn't fit easily into this table, and that's evaporation, something we're somewhat familiar with, but we want to go into a little bit more detail. So we'll start off with the energy aspects at the molecular level from the different phases. And there's nothing should be really surprising about this, but we just want to shore up some of the details. So we're going to look at really in these energies, its relative values, okay? Not so much absolute values, because if you have a lot of something, you can up the amount of energy, even though relatively speaking, there's not a whole lot of kinetic or potential. Okay, so a solid, well, we can deduce why this should be if you had to explain it. If we start down here somewhere in the solid phases on our chart and we go up to gas phases, to get from point A, if you will, to point B, we know we have to input energy. So if we're inputting energy and we're having temperature rises between phase changes, then we know that a kinetic energy is going up. So that stands to reason that a solid has a relatively low and a gas has a relatively high. And we can, of course, say a liquid is somewhere between moderate, medium, whatever you want to call it. And then from a potential energy standpoint, we would expect essentially the inverse. A solid, because the molecules are close together, they're in a crystalline form, there's going to be stronger intermolecular bonds, so we're going to have a high negative potential energy. Okay, so it's like in a deeper and deeper well. Whereas a gas, we can go so far as to say that there is zero potential energy between the molecules. And that's an important supposition when we develop the kinetic theory later in the next chapter. So of course, again, liquid is going to be like, we call it the baby bear, right? Somewhere between moderate, not too hot, not too cold. So with potential energy goes molecular separation. And again, the diagram below kind of gives you an idea. This isn't much of a surprise. So we have a low molecular separation. Again, the baby bear, moderate, and here we're going to have a high molecular separation. And then lastly, the effect on the surroundings. So what do I mean by that? So let's take water. Let's say water is in the liquid phase. Okay, so we're somewhere here, and we're about to enter. We're going to freeze it. So we're going to go to the solid phase. We're going this way on our diagram. So what does that mean? Well, take the water, you're removing internal energy from it. You're pumping it out, if you will, going against nature in terms of a heat direction. So if you're taking internal energy out of the water to make it freeze, then you're dumping it into the surroundings. So you're adding energy to the surroundings. This would be a warming effect, which is not necessarily something you'd think of off the top of your head. When I say I freeze something, you might even think by default, well, I'm cooling my surroundings. No, you're actually warming your surroundings. If you don't fully appreciate that, look at the back of your refrigerator. Okay, in the back of your refrigerator, it's warm because you're dumping, if you will, heat from the inside, leaving the inside cooler or frozen, and dumping it to the outside. Same with an air conditioner. So on the other hand, melting, which is going from solid to liquid, is a cooling effect. Okay, that's a little less obvious. So if you apply the same reasoning, if we go to the vaporization and condensation phase, okay, boiling, you should be able to do like freezing. In order to boil something, like melting, if you want to boil something, you have to take energy and input it into the material that you're trying to boil. So that's going to take energy out of your surroundings, and that's going to be a cooling effect. And then condensation or condensing would be a warming effect. In fact, anytime you step out of the shower and that bathroom is filled with steam, okay, that steam is condensed water, because it's technically not steam, it's really water vapor. That has a warming effect in the bathroom. It's much less cool in the bathroom when you have all that steam air in the atmosphere. That's a very, very important process. When you have those water vapor rising, and then eventually condenses to clouds, it releases a tremendous amount of energy into the atmosphere, which can stoke storms and weather phenomena. Okay, so there's a nice summary of your phase changes in terms of the energies. So let's finish up with evaporation, which is a form, or it's basically turning a gas into a liquid. Okay, but it's very different than boiling for reasons we're going to talk about. But one thing we do know about evaporation, it is a cooling effect. Okay, a very, very strong cooling effect. And going back to stepping out of a shower or even a swimming pool, when that water evaporates from your skin, especially if the air surrounding it is dry, you'll start shivering considerably. And that's extremely important for your body temperature regulation. Okay, so what makes evaporation different than boiling, right? So they're both liquid to gas. All right, so what the main thing that distinguishes evaporation from boiling is really the first point. It can occur at a temperature below the boiling point. So when you're talking about boiling, you're at a specific temperature. Okay, with evaporation, you can have water evaporate at just above freezing if the conditions are right. Okay, you can certainly have it happening when you're near the boiling point, but not at the boiling point. Why does this happen? How can this happen? Well, if you look at the diagram down here, you can kind of get an idea of what's going on with evaporation, all right? First of all, it's a surface effect. It does not happen throughout the liquid, which happens with boiling. When water starts to boil, the whole thing starts to boil. Not all at once. It doesn't just vaporize in an instant. It takes time, but it's not occurring just at one place. Evaporation is at the surface. And why does it happen at the surface? Well, you got to imagine that these molecules right here are jiggling around with some degree of freedom in their motion. And every so often, the conditions will just be right that the molecule near the surface has enough kinetic energy to escape. Okay, so it's really a probabilistic effect. So when those escape, what you're going to leave behind are molecules that have a lower kinetic energy on average. And since there's a lower kinetic energy on average, the liquid is going to cool. Because one definition of temperature is the average kinetic energy of your molecules. Okay, so the faster ones escape and leaving the cooler ones behind, they jostle and jiggle each other, and every once in a while a collision occurs where one gets enough kinetic energy if it's at the surface to escape. And it's a very, very powerful cooling technique. In fact, remember we talked about the BEC, the Bose-Einstein condensate, which is a form of matter that only occurs when you're a millionth of a degree above Kelvin. Well, how do we get temperatures that low? Well, one effect, and people won Nobel Prize for this, is using very clever forms of evaporation. You take a small sample of atoms, let's say in the order of thousands or tens of thousands, which is tiny, and you trap them in a magnetic field, and you lower the threshold of the magnetic field so that the faster moving molecules can escape that threshold, leaving behind those that are barely moving, and you get a very powerful cooling effect. So there's a lot to be said about evaporation as a important and very effective way of cooling. All right, so how do we affect the rate of evaporation? What if we want to increase or decrease it? Okay, so surface area is a big factor, right? The more of the liquid you have exposed, the more surface is exposed, and you can have things evaporate. So on a lake, you get a rapid evaporation. If you take the same lake and make it really, really deep and not so wide, evaporation is obviously not going to occur as much. Perhaps more obvious, temperature. The warmer you are, the faster it occurs. But it can occur at any temperature. Moving air. Well, there's wind, right? Why do you put clothes out in a clothesline if you still do that, or people still do that? Because the moving air gives those molecules near the surface kinetic energy, allows them to escape, a very effective way of drying. And then lastly, a decrease in air vapor pressure. Okay. In other words, you're not pushing down on the surface, so the molecules, again, have a better chance of escaping. All right, so that sums it up for the basics of phase changes. We will work on practice in class, and I'll talk to you another time.